Alright, welcome to Lecture 2, Le Chatelier's Principles. This will be a continuation of our chemical equilibrium unit. The essential question for this is, how does Le Chatelier's principle affect the equilibrium position? Now, if you recall from Lecture 1, when we talked about the equilibrium position, remember that when an equilibrium has been established, the reaction will either be product favored or reactant favored. If there's more product than reactant, then the position of the equilibrium is to the right. But if it's reactant favored, meaning that there's more reactant than product, then the equilibrium's position lies to the left. All right? And so that's important to remember as we go through Le Chatelier's principle here. Now, Le Chatelier's principle pretty much is this following statement here, which should be written down in your notes. It says, when a system at equilibrium is subject to a change, so we've already established an equilibrium, and it goes through a change, it will respond in such a way as to counteract, and that's an important word that I would highlight, is counteract the effect of the change. So simply put it, this means that whatever we do to the system at equilibrium, the system will respond in the opposite way. So what we're referring to this is basically this idea. If I add a reactant to an equilibrium situation, then the reaction will try to eliminate that reactant. If I remove reactant, then the equilibrium will respond by creating more reactant. If I increase the temperature of the reaction at equilibrium, then the reaction will change in such a way to reduce the temperature. The idea is that anything I do to the reaction, it's going to do the opposite of what I do to try to counteract it. And that's the important point of Le Chatelier's principle. All right, so now let's look at some specific incidences where this will occur. So we're going to start out, first of all, looking at concentration and the effects of the equilibrium position when I increase or decrease the concentration of either the reactant or the product. So let's say that we have a particular reaction here. Let's say we have a reaction, a simple one like 2HI, and it's in equilibrium with its products, which are going to be H2 gas and I2. Alright? Now remember, the idea of Le Chatelier is if I change the concentration of a reactant or a product, it needs to do the opposite, or the reaction will do the opposite of what I do to it. Okay? So, for instance, these points up here that you should probably put in your note is the addition of a reactant. So we're adding a reactant. It's going to shift the equilibrium to the right to reduce the amount of reactant. Okay? So let's kind of think about it in this terms. If I add more HI, so I'm adding more HI, the reaction wants to reduce it. So in order to reduce it, the reaction needs to go in the forward direction at a faster rate. And so the reaction in the forward direction speeds up, and therefore the equilibrium is disrupted, and we say that the equilibrium is shifting to the right. Alright? So again, if I add more reactant, the reaction shifts to the right in favor of making more product and eliminating the added reactant. Alright? So think about it in that terms. Now, what would happen if I reduce the concentration of a reactant? Well, if I reduce the concentration, the reaction wants to do the opposite, so it wants to make more reactant. I lose reactant, the reaction wants to make more of it. So if it does that, then if I remove HI, the reaction is going to shift to the left, essentially, to increase the amount of reactant to make more. So that means the reverse reaction is going to speed up and go faster to make more HI. Alright, kind of seeing how that works? Alright, well, let's look at in terms of product now. Alright, same kind of situation. If I add more product, then the equilibrium is always going to shift in the direction to reduce the product. Well, the only way to do that is to shift it in the reverse direction. So if I'm adding more product, then it's going to shift away from the product to create more reactant. And so it shifts to the left, essentially. But if I reduce the concentration of the product, then the reaction wants to make more of it. So which direction would the reaction shift in order to make more product? Well, it's got to shift to the right, of course, and that means it's going to speed up the reaction in the forward direction to create more product. So as you can see, anything that I do to the concentration, the reaction does the opposite in order to either reduce it or create more. Alright? And so that's essentially how Le Chatelier's principle works with concentration. Now what about temperature? Well, let's say we have a reaction here. Again, let's say we have a reaction of A plus B, and it's going to produce C. And let's say that the reaction delta H is negative, and so this is an exothermic process. Now, to help you to understand what happens when temperature changes, you need to understand if the reaction is endothermic or exothermic. So since it's exothermic, heat energy is being released. Now, to make this easy for you, this is what I would redo. I would go ahead and rewrite my equation. I would write out the reactants, A plus B, going to C, and then I would go ahead and add heat energy to the product side. Now, why would I add heat energy there? Well, it's because we know that the reaction is exothermic, so heat is being released, and therefore it should be on the product side. Now, by doing this will help me to understand which way the equilibrium is going to shift if the temperature changes. Alright? So let's say that I add more heat energy. Well, according to Le Chatelier, if I add more heat energy, then the reaction is going to shift in a way to reduce the heat energy, right? And so that means that by adding heat energy, the reaction should shift towards the reactant side to reduce that amount of heat energy. All right? And so the equilibrium will shift to the, in this case, will shift towards the product or reactant side, which is the endothermic direction. Right? If you think about it, if the forward direction is exothermic, then the reverse direction must be endothermic. So by adding heat energy, we want to get rid of it, and so it shifts in the endothermic direction. Alright? As stated up above here, when heat energy is added to an equilibrium system, it will shift in the endothermic direction. Alright? Alright, so now let us say, let us think about this now. Same reaction. We know that the forward direction is exothermic. Alright? Fact is, I probably need to write an equilibrium here. So, what if I remove heat energy? If I get rid of some of the heat energy? To reduce the heat energy, I have to lower the temperature. So if I lower the temperature to reduce heat energy, then the reaction wants to make more of it. So if it wants to make more of it, the equilibrium is going to shift to the side that produces more heat energy to raise the temperature. So it's going to shift in the forward direction in this case, or what we would say the exothermic direction. So as stated above, when we reduce the heat energy, the equilibrium will shift in the direction to produce more energy. Alright? Now, let's look at a different situation. Let's erase all of this. Now, let's say, again, we have a reaction, and we're going to take A plus B, and it produces C plus D, and it's a reversible reaction, so eventually it'll establish equilibrium. Now let's say that the delta H is going to be positive. So what does that mean? Well, that means that in the forward direction, the reaction is endothermic. So now in this case, I'm going to put heat energy on the reactant side, plus A plus B produces my equilibrium with C plus D. Alright? So now we know that the forward direction, it is endothermic, and then the reverse direction must be exothermic then. Alright, so now let's treat heat energy kind of like we did before, and you can kind of think of it now in terms of being a reactant. So even though it's not really a reactant, you can kind of think of it in that way in these terms. So if I add more heat energy, which way is it going to shift? Well, if you said that it's going to shift towards the products, you would be right. Because if we add more heat energy to this reaction, it's going to want to get rid of it, so it's going to shift it towards the products, and it's going to favor the endothermic reaction, alright, to get rid of it. But what if we get rid of some of the heat energy? In other words, we lower the temperature down. Well, if we lose some heat energy, we want to make more heat energy. Well, the only way we can make more energy is to shift the reaction to the right towards the reactant side to create more heat energy, which is really in the exothermic direction. Alright? So you really need to think about this. I know sometimes the first time you're exposed to this, it takes a little bit of time to think about and reason these problems out in your mind. Okay? But this is what essentially is happening when you have a change in temperature to an equilibrium. Alright? Now, let's go on to pressure and see what happens with pressure. Now, pressure is only going to be affected if you're dealing with gas molecules. Alright? So let's say that we have a gas here. Gas A and plus B, and we make C. Alright? Now, what you have to make understand here is that there's more reactant molecules. There's 2 moles of A gas versus 1 mole of B gas. Okay? So there's more moles of reactants than there is of products. Okay? Now this is going to have a significant impact. Okay? So if the reaction equilibrium is subject to an increase in pressure, right? So we increase that pressure, the system will respond to decrease the pressure. Alright? So again, it wants to do the opposite of what I do. So if I increase the pressure, the system wants to reduce the pressure. So how is it going to do that? Well, it's got to reduce the pressure by shifting the equilibrium to favor the size with the smallest number of molecules or moles. Alright? So in this case, if I'm increasing the pressure, it's going to shift to the product side where there's a smaller number of molecules to reduce the pressure. Alright? Now, if I reduce the pressure, so if I decrease the pressure or reduce it, then the equilibrium is going to shift to the position where the side with the larger number of molecules, because that will create more pressure. The more molecules you have, the more pressure, or the higher the pressure. So, if I reduce the pressure of this system, then the equilibrium will shift itself to the left in order to create more molecules, which will increase the pressure. So you kind of have to think of it that way. So let's talk about this one more time, okay? In this reaction, if I increase the pressure, the system wants to reduce it. So the equilibrium will shift to the right in order to reduce the number of molecules, which then reduces the pressure. Alright? Small number of molecules, small amount of pressure. Okay? Now, if I reduce the pressure, then obviously I want to create more pressure. So the only way I can create more pressure is that if this reaction shifts to the left in order to create more molecules of reactants, and that will increase pressure. Alright, so that's how pressure works at equilibrium changes. Alright, now the last one I want to look at is how do catalysts affect the equilibrium position. So the reaction is going, I throw in a catalyst, and how does that change the equilibrium? Does it shift it left? Does it shift it right? Well, it turns out a catalyst has no effect on the equilibrium position. So a catalyst does not change the position of equilibrium. The only thing it does is allows us to achieve equilibrium more quickly. Alright? So by adding the catalyst, it speeds up the rate of the reaction, both the forward and reverse, apparently, and so therefore we get to the equilibrium faster. And that's all that a catalyst does. Alright? So one more time, a catalyst does not affect the equilibrium position at all. All it does is speed up the rate at which we establish or achieve equilibrium. Makes it go faster. Alright? And so there basically is Le Chatelier's principles in a nutshell, and the different situations that could arise on the quiz, concentration changes, temperature changes, pressure changes, and adding a catalyst and how that might affect the equilibrium position. So make sure that you are very familiar with this lecture. Be ready for the quiz on it. And that is really it for now.